Okay, so this is our fourth video in our 1D Kinematics series. In this short video, we're going to take a look at a couple of examples. And these examples would be sort of characteristic examples that you guys might find on an assignment or maybe on one of the term tests or the final or something. So let's take a look at two of them here. We're going to start off with this first example of a car merging into traffic. This is example 2.13 from the text. And let's give it a read here. So a car merges into traffic from a ramp. Its initial velocity at the entrance to the ramp is 10 meters per second, and it accelerates at a constant 2 meters per second squared. How long will it take the car to get 200 meters up the ramp? Okay, so normally I like to draw a little diagram here just to make sure that we have the idea of what we're doing. So let's imagine that this is some sort of a ramp. This can be like a highway here, let's say. And so some car starts off here. And the car starts off, we'll call this x0 equals 0. We'll say it starts off with a v0 of 10 meters per second and an acceleration of 2 meters per second squared. Okay, and so it's accelerating and moving in this direction here, and we want to know how long it takes to get to x equals 200 meters down the ramp here. So before it merges onto the highway, right? This is the highway. There's other cars moving along like this. Okay. So maybe a nice way to start to start looking at the problem is by making a little bit of a table here. Sometimes that's helpful. So initially we have our v0 equal to 10 meters per second. We have our acceleration equal to 2 meters per second squared, and our initial position is 0. And our final, we have a final velocity. Well, we don't know what the final velocity is. Maybe we'll find it out sort of as we're going through the problem, but it's not important. It's not what we're being asked, so we don't need to find it unless we kind of accidentally find it. Our acceleration is constant, so that's just going to be 2 meters per second squared. It's constant for the whole problem, and that's good. It kind of has to be if we're going to apply these equations, right, that we're going to be using here that we developed in the last video. And our final position, our x, is going to be equal to 200 meters. What we want to find t. Okay, and we want to find the t that corresponds to us being at an x of 200 meters. Okay, so really what we want to do is we want to find an equation from the equations that we developed in the last video that relates all these variables that we know, or any combination of them, so v0, a, x0, or x, or all of them together, to t. And ideally we would like it to be an equation that only has t as an unknown, so we can solve for t. And we can find one of those equations, equation 4, from that collection of equations will do the job for us. And so let's remind ourselves, equation 4 tells us that x equals x0 plus v0t plus 1/2 at squared. And so if we substitute in numbers for these values, we can just copy them down from our table above. So we're going to have 200 is equal to 0 plus 10t plus 1/2 2t squared. And cleaning that up a little bit, I'm going to clean it up and I'm going to rearrange it so that we can solve the quadratic. So we should all recognize that this is a quadratic in t. We have our linear term here and our quadratic term here in t. And so we want to solve for t. So if we clean this up, we can rearrange it to look something like this. We can simplify the coefficients out of the t squared, out in front of the t squared. So it's going to be 1t t squared plus 10t minus 200 equals 0, right? And if we call this a, not acceleration, but the a that we're going to use in our quadratic formula, and we call this b, and we call this c, then we know we can solve for t using the quadratic equation, which I'll write down over here. So we can solve for t using this quadratic equation. Let's substitute in values. And if we do that, we're going to see that we get the following equation. So b squared minus 4ac, well, minus 4 times 1 times minus 200, well, that's just plus 800 over 2. And this is just equal to minus 10 plus or minus, it's going to be the square root of 900, which is 30 over 2. And so this tells us that t is equal to, it's 10 or minus 20. And so this is often going to happen when we apply the quadratic formula. We're going to get two different answers. In some cases, both answers will be physical, and we're going to have to choose which one we want. In this case, minus 20 seconds, we're not really interested in that time. That's an unphysical answer. So it's clear that we really want this result here. But other times we might be interested in both of the results that we get, and we'll see some of those problems later on. But for now, the answer for this question is just t equals 10 seconds, and that's our final answer with units. Make sure we always have units in our final answer. And so that's the answer. It'll take 10 seconds for the car to get 200 meters down the ramp, given these parameters that we have set forth here. Okay, let's take a look at a second example now. So in our second example, we have a racer or a runner. At the end of a race, the runner decelerates from a velocity of 9 meters per second at a rate of 2 meters per second squared until she comes to a stop. We definitely want to make sure we read these problems twice, because this last point, this until she comes to a stop point, is going to be very important. Because if we apply this 2 meters per second squared acceleration for longer than the time it takes her to come to a stop, she's going to be moving in the opposite direction. And here I'll draw a picture that'll kind of demonstrate that a little bit. So we can imagine our racetrack here. This will be our finish line. And so the racer gets to the finish line. At this point, she has an initial velocity of 9 meters per second, but an acceleration pointing in the opposite direction, right? She's slowing down, so we're going to say a is equal to minus 2 meters per second squared. We're going to call this our x-axis. And so we want to know how far down the track she's going to travel in the next 5 seconds. Now, we have to be careful, because if she comes to a stop and we keep applying that acceleration, let's imagine she's running in this direction, she'll come to a stop somewhere here, and if we keep applying that acceleration, she'll keep moving backward until the 5 seconds have elapsed. So we need to be careful about that. Maybe we'll start off initially by calculating the time that it takes her to come to a stop, and we know that's the end point. After she comes to a stop here, that's it. She won't move any further, because she's only decelerating at 2 meters per second squared until she comes to a stop. Okay, so let's calculate that. We want to find an equation that's going to give us the time at which she's going to come to a stop. And if we look at our third equation that we developed in the last video, we're going to see that it looks like this. And we can clean this up a little bit. We want to solve for the time that she comes to a stop, so we're going to have v minus v0 over a. is equal to t. And if we substitute numbers in now, well, we know that v, we're interested in the time that she comes to a stop. So at that time, v will be 0. And so substituting in numbers, we have t equals 0 minus our v naught, which is 9, over the acceleration, which is minus 2. And this gives us a t of 4.5 seconds. And this is an intermediate result. This is not the final result that we want, but this is going to lead us to our final result. So we found that at 4.5 seconds, she will have come to a stop. She'll be at this point here, the stopping point. And we don't want to apply the acceleration beyond that point because she'll be heading back in this direction in that case, and that's not what we want. The problem tells us that once she comes to a stop, that's the end of the deceleration. Okay, so let me cut this off here. And then, given that we have a t equal to 4.5 seconds, and the other, well, we had a v naught of 9 meters per second, and an a equal to minus 2 meters per second squared. We want to find what distance she covers in this time. So now we want to use an equation that takes these variables in and is going to give us a final position out, right? So basically what we want is we want x, and we've set this this finish line in a sense as our x naught equals 0. So we can include that here. And from these variables, we want to be able to solve for x. X will be the stopping point, right? So if we look for an equation that contains v naught, a, x naught, and t, from the equations from last time, we'll see that we could use, and I'm just going to repurpose this x that I've put here. We could use x equals x naught plus v naught t plus 1/2, at squared. And then simply by substituting in values, we can see that we're going to end up with the following equation. Right, and now it's just a simple matter of solving for x. So we can pull out our calculators at this point, and this ends up giving us 20.25. And so the answer here is going to be x equals 20.25 meters. And that would be the answer to part A here. And actually this should be a B. Sorry about that. Okay, and part B is actually very easy to answer. What's her final velocity? It's kind of a setup a little bit, because if we hadn't been careful and we had applied this negative acceleration for 5 seconds, as this part A is kind of hinting that we might want to do, then we would find that she would have a negative velocity afterward, right? Because she would have decelerated and come to a stop at 4.5 seconds and then started going back up the track. But because we did it carefully, we're going to see that in part B, well, we know that her final velocity v is just 0, right? She stopped at 4.5 seconds and she didn't start going again. And so that's the solution to that problem.